Ash, thank you very much for that introduction, and thank you to Cywen for this opportunity to present. I've cancelled my video because I'm having some broadband issues. Has that slide changed? So what I'm going to talk about is the phosphorus recovery process that we adopted in the Ringsend wastewater treatment plant.
Your slide hasn't changed, Dara.
I see that, Barbara. Anyway, I'll keep talking. So, and I'll keep trying to change the slides. The Ringsend wastewater treatment plant is Ireland's largest wastewater treatment plant. It was designed originally for 1.64 million PE as an average daily loading for wastewater treatment, and it due to a number of demands, it has to be upgraded to 2.46 or 2.4 million PE loading as an average daily loading. 2.46. The drivers for that are that there's increased load on Dublin, which is obviously our biggest city, but there's also a change in the EPA applied more strict effluent standards than the original treatment plant was designed for. Have the slides changed yet? Just checking.
Not yet.
Sorry about this now. So anyway, I'll keep talking. So the Ringsend treatment plant, as I say, is so the two main parameters that drove a capacity upgrade at Ringsend are a total nitrogen of 10 milligrams per litre and a total phosphorus of 1 milligram per litre. These means that the actual treatment capacity of the plant more or less effectively doubles. So to provide treatment on the site, which is a very constrained site, there was a need to look for a treatment process that could upgrade the capacity within the existing site. And the existing site, as I say, is constrained, and you may know the site. It has 2 tiers of sequencing batch reactors, 12 on top of 12, and there's very little space on that site for any future capacity. There was about 0.8 hectares of space retained on the site. So when we were looking at treatment options, the aerobic granular sludge treatment process, or the Nerida process, was evaluated and seen as a process that could upgrade the treatment plant on the existing site. So Irish Water adopted, or the process proved that treatment process and selected it as an upgrade option for Ringsend. The slides are still not changing. Something wrong with my broadband. I keep talking. So as part of the AGS treatment process is a biological N and P process. Therefore, the bio-P is removed biologically and retained in the waste sludge in the treatment. And that waste sludge then is processed through our sludge treatment process, which is thermal hydrolysis, anaerobic digestion, and thermal drying. So in the anaerobic digestion, being anaerobic, phosphorus is re-released from the sludge, and that re-release would get recirculated around back to the influent load, and cause that recirculation was going to cause an issue in terms of meeting the 1 milligram per litre phosphorus requirement. So it was realized, or not, it was part of the process, was to need to kind of recover or remove phosphorus in the process. The slides are just not changing at all. I'm going to just okay, I'll keep talking. Sorry about this. So we looked in doing that, because we have to meet the 1 milligram ELD for total phosphorus. We looked at a number of removal processes to remove phosphorus from the treatment plant. from the treatment process to stop that recirculation and impact on the 1 milligram ELV. And the three kind of high-level processes we considered were going back to chemical dosing, which using ferric, which wasn't really, it was a very high-level option when we had to rule out. But then we looked at recovering phosphorus from the sludge liquors line and from the actual sludge line itself. So in evaluating these processes, the first one being the other consideration when we were doing all of this was looking at the kind of regulatory environment that we were working in. So in terms of, as Asik has said, that phosphorus was defined as a critical resource within the EU. Also based on the German experience that where they're requiring phosphorus removal on all plants above 50,000 P by the end of the decade, it's likely that phosphorus recovery will be could be an EU requirement. And also one of the things we also considered was end of waste. Because when you recover struvite or struvite from the treatment process and convert it into a fertilizer, you need an end of waste requirement. The other things with phosphorus recovery is that in terms of the anaerobic digestion, it can produce struvite in the process, which can block up pipework and thickening plant. So with anaerobic digestion, when you have a P limit on the ELV, struvite becomes an operational issue. And then also there was a consideration that struvite, if recovered, is obviously a valuable process anyway. And as RIN treats 40% of the wastewater for Ireland, it was considered a key site to look at in terms of recovery and reuse of phosphorus. So as I say, we looked at the three processes: the chemical treatment, which really is about dousing ferric into the process to recover.
Dara, just a quick ferric thing. Can you unshare your slide and then reshare again, just in case if it will work?
Yeah. I'll stop sharing. Yeah.
And try to reshare again, please.
Sorry about this. Has that reshared?
It's coming up probably. Just taking. Yeah. It's working, I suppose.
Oh,
yeah.
Good man. Thank you. So that's the wastewater treatment plant. You can see the SBRs, the very tight site, and the two yellow areas are where we had space for upgrade. I just catch up with myself. So struvite management and the use of product are our secondary drivers, and the ELVs were our primary drivers. And then this is the consideration in terms of the legislative background. Have I missed anything? Well, peak phosphorus in 30 years is as Asik has said, it's a limited, phosphorus is a limited resource. So we're looking at these three options here. And chemical dosing, the chemical dosing option would impacts on the granule growth in the AGS process. So it would mean that we would have to increase the number of AGS Nerida tanks that we're installing. So just to go back on that, the plan originally was to retrofit all the tanks to aerobic granular sludge, all the existing 24 tanks, and build 6 new tanks. However, over process proving, we were able to develop a hybrid solution. So we were converting the top 12 tanks to AGS, and the bottom 12 are a hybrid AGS solution. So if we went with the chemical dosing here, we would have had to convert another block of 4 to AGS because the chemical dosing impacts on the growth of granules. It would also add about 15 to 20% more sludge in terms of inert sludge, which would affect our digestion, and we would need to build an additional digester capacity. And the chemical dosing in itself is just very, very expensive. So when we looked through all that, that was just ruled out just on very quickly on a whole life cost basis, but what needed to be done. So the next two, the two main options, because they were demonstrated at scale, were the sludge line process and the sludge liquors process. So I'll just go through these. Sludge line process will sludge directly from the sludge after digestion, and it fits into the process downstream of digesters and upstream of the dryers. It produces a struvite type material that can be used in fertilizer production. It's not a direct fertilizer, but can be used in fertilizer production that needs further processing. It obviously protects the sludge line from excessive struvite formation, and that was one of our secondary drivers. However, it would use a lot more chemicals than the sludge liquor process. It recovers less phosphorus than the sludge liquor process. And because of that, it is estimated that the amount of P in the biosolids would increase from 1.5% to 2.3% in the sludge that we're reusing from Ringsend on farmlands in the south of the country. And that increase in sludge, or phosphorus in the sludge, would have implications on land spreading. We would just basically need more land, and that has a kind of an implication on cost. The big benefit from the really big benefit is it has a much lower capital cost, the sludge line process. The sludge liquors process removes phosphorus from the sludge liquors, so you combine the liquors from the primary and secondary thickening. It recovers almost double the amount of phosphorus than the sludge line process. Fits into the process in the sludge liquors management area. It produces a struvite material that can be used directly as a fertilizer, so it's already ready to use as a fertilizer on the market. It obviously protects sludge line from excessive struvite formation. It uses again a lot less chemicals than the sludge line process, and it has a smaller impact on the sludge mass in the sludge that's being reused on land, which again, it provides a bit more robustness on the spread land out, which doesn't challenge it as much. However, it has a significantly higher capital cost. So in doing an evaluation of those two processes, we're taking into account the value of the struvite product from each stream, the cost of chemicals, the energy costs, operator costs, and doing quite a detailed analysis and sensitivity on those costs. And one of the times when we were actually doing the sensitivity back in late 2019, early 2020, the value of phosphorus on the world market had dropped to a 10 or 11-year low, and that actually changed the kind of point at which the crossover between the two processes came, and it was pushing it much more in favour of the sludge line process. But given that it was an 11-year low, we took a view that even with that pushing out of the crossover between the two processes, that the sludge liquors process was the selected process. And this is really based on particular conditions for Ringsend, the drivers that we were looking at, and the ELBs that we're meeting. So it was a particular evaluation for the Ringsend conditions and the volumes and the cost of each process. So what we've ended up with going ahead with is a contract with Ostara for phosphorus recovery fixation, and this covers the design, construction, and installation of a Ostara system, including reactors, chemical dosing, crystal harvesting systems, ancillary equipment, pipework, all of that sort of stuff. And it includes for the design and construction of storage for the facilities for both chemicals, because the chemical demand on these processes is very high. And then there was enabling works, sludge liquor pumping stations, rising mains, etc., and connection of electricity and potable water. And our last speaker today, Matt Goodman, will be going into more detail on the Ostara process. So really, that's kind of the end of my presentation. There's possibly a bit of time for questions, maybe not at this stage. but because I've gone beyond. Sorry about the glitch at the start there, and we can take questions either now or at the end.
Thank you very much, Dara White. That was very informative and very nice presentation, especially on the case study for a upgradation of a wastewater treatment plant in Ringsend. I'll just remind all the participants, we'll take questions towards the end of all presentations. So please type your question or comments in the Q&A facility, not in the chat, and we'll address those after the end of the presentation. So I'll move to the next speaker, Dr. Patrick Forrestal. So Dr. Patrick Forrestal is a senior research officer in the Crops, Land Use and Environment program of Teagase, based at Johnston Castle in Wexford. Patrick grew up on a grassland and arable farm in Ireland. He earned his bachelor degree in animal and crop production and master's degree in crop science from University College Dublin. Patrick received his PhD training at University of Maryland in USA while working in the area of field crop nitrogen management. His research group focuses on plant, soil, and nutrient interactions, including the agronomic and environmental performance of new mineral and bio-based recycling fertilizers and manures. He has published extensively with his team and is an active partner in several national, EU, and international collaborative projects with researchers and industry. So please, I would like to welcome Patrick Forrestal. Please unmute your mic and take the floor for your presentation. Patrick, over to you.
Thank you, Ashik, for the kind introduction. I'll just go ahead and share my screen here. And should be coming through to you now. So do we have a starting slide? Okay.
That's fine, yeah.
We're in business. Okay, so it's a pleasure to be joining you this evening. So I'm going to talk a little bit around the reuse of recovered phosphorus, I suppose more with a focus on the agronomic side, its use in the field, is there a need for it here in Ireland, and what we're doing in Teagase. So hopefully that'll be of interest. And I want to acknowledge my team, particularly Ashik, Cathal, and John, who've done a lot of the work with this topic in the field, and collaborators, including Niamh Power, and I'll touch on one of her papers that's recently come out. So just by way of introduction, very quick, our team focuses on, as Ashik mentioned, both conventional and new mineral fertilizers along with bio-based fertilizers. So it's quite a bit of what we do, that recovery side, which some of you may be working on. And I suppose we look at all the aspects through from the agronomy, also losses to water and air, and effects on the soil. So let's kick it off with just on the topic of, is there a need for phosphorus that you might recover from waste streams for land use? And certainly based on this paper here, which we've recently published with Niamh Power, an overview on the deficit and requirements of the Irish soil balance. And so what is highlighted in this paper is that, based on the county by county data, a lot of our Irish soils, as much as 63% of them, have agronomically suboptimal levels of P for plant growth. Now, it's worth noting that we might not want to increase the phosphorus in all of those soils to an optimal level. Some of them might be in low intensity uses, for example, or it mightn't be as favorable for intensive agriculture. Maybe that's not something we want everywhere, but nevertheless, it just gives you some illustration of the need for phosphorus. And annually, about 43,000 tons of P fertilizer are imported into Ireland, mineral P fertilizer to be applied to agricultural land. So certainly if we can recover more phosphorus from wastewater streams, that can help to offset some of that fertilizer. So I might circulate actually some of the papers that I mentioned, and maybe those could be sent on to the participants. But you can see here in the graphical abstract a couple of things coming out. that in terms of indigenous, potentially recyclable phosphorus, there are differences around the regions, but this orange section here is from sewage sludge, and the grey is more relating to water and recovery of phosphorus from water. And that differs around the country, but obviously Dublin with a higher population, they're having more in this section. But wherever we go around the different regions of the country, the blue bar indicates requirements against, let's say, what's readily recyclable. So there's a gap there to be filled. So certainly there's a need for this phosphorus. And where does the conventional mineral fertilizer that we're currently using come from? Well, the Irish, what comes into Ireland doesn't necessarily come from this particular mine, but this is the Mosaic Phosphate mine in Florida, which I had a chance to visit a number of years back. And this bucket of this dragline device here, was picking up more than 100 tons of material at a time from essentially an open cast mine to take out the phosphate rock. And that was essentially put through a giant liquidizer to be pumped to this plant where the phosphate rock was separated out and sent on for further processing into fertilizer. So of course, this is really important for us in agriculture that we can access this type of material. But in Ireland and at a European level, we rely on importing this phosphorus. And it really brought home to me that visit that anything we could do to recycle phosphorus, we should be doing, while we're still going to, in reality, need some of this mineral fertilizer. And if you're recapturing phosphorus, one of the things that you're going to have to compete with at a farm level is the cost of the mineral fertilizer. But the good news is, as you can see from this graph, that phosphorus fertilizer, as a nutrient, if you're recovering it, it's more valuable than nitrogen and phosphorus, for example. I came across this nice study which looked at, so it's 10 years ago now, right? But it looks at this power versus interest matrix on the topic of adoption of use of recycled or bio-based fertilizer products. And if we look along the interest axis, people like me, scientists, we might be very interested in this. Maybe recycled fertilizer companies are very interested in it. And then they also look at this power matrix. So where did various actors fit on this matrix at that time, according to this study? And you can see national government there up with having a lot of power, but maybe not as far along the interest scale. But I think this is really changed in the period. If we look at what's coming out of national government and the EU Commission recently, we've got this national policy statement on the bioeconomy from the national government, where they're really talking about using resources that were previously discarded and putting them to more productive uses, including in farming. And recovery of phosphorus from wastewater streams is really a very good fit with this. Also at the European Union level in 2020, we had the Farm to Fork strategy coming out, and they talk about use of advanced biorefineries to produce biofertilizers. So, Dara in his talk talked about different processes which could up the peak content of material, and even that some of those would form the feedstocks for further processing into bio-based fertilizers. But certainly the mood music is there, and the objectives are set out to have this recycled bioeconomy driven forward in the coming years and decades. So what are we doing at Teagase? As part of an Interreg and an EU Horizon 2020 funded project, we're looking at the use of a number of different recycled phosphorus based biofertilizers, and looking at how do they perform in the field for plant and soil availability, and how might they be integrated into a fertilizer program? Because at the end of the day, this is going to be essential for how a farmer would use it, and with an increased focus on the environment, those fertilizers have to fit into a nutrient management plan. And to do that, we need to know how available they are to the plant. There's a little video here on YouTube about the Nutri2Cycle project. If you punch Nutri2Cycle into YouTube, you can have a little look if you're interested. And we have a track record in this area and we've recently published this particular paper here looking at both phosphorus and nitrogen fertilizer replacement value dairy processing sludge. So, it's not all about phosphorus. Often recovered streams contain different nutrients, and this is an example where there's nitrogen in there as well. Maybe it's not the main value, but we still need to know how available that nitrogen is. So if we look here, in comparison to calcium ammonium nitrate, which is a standard mineral fertilizer that a farmer would use, set at 100%, how available was the nitrogen that was in these various different sludges? And you can see, I suppose the first thing coming out is that there's quite a difference, right, between the different processes in terms of how available the nitrogen is relative to CAN. So the sludges, they're not all the same, and also they're not as available. So a farmer needs this information to know how much extra mineral fertilizer he would need to balance up to meet crop requirements, and to make sure also that he isn't in excess or in deficit. Again, another recently published paper from this year where we looked at the relative P effectiveness of 2 dairy sludges where phosphorus was recovered relative to superphosphate mineral fertilizer, which is triple superphosphate based fertilizer that's used here in Ireland as a straight phosphorus. And we see here that, again, at least in the first year, these are not as available as the superphosphate fertilizer. And we've more extensive work currently going on, and Ashik is actually working on writing up this at the moment, so there's more to come here, looking at a broader suite of different products over a longer period. It wasn't available in the first year. What happened if we kept going for longer? And we have 2 struvite materials here, one from potato processing, one from sewage sludge, and obviously struvite's a process that can be applied to different wastewater streams, and they have 5 to 6% P content. And that P content does have a big practical implication in terms of transport. And I've just put the example here of if you're a farmer wanting to apply 20 kilograms per hectare of P, which they would often need to be doing, and for cattle slurry, obviously the volume is very large. It's very large. We look at larger volumes, 37 tons per hectare. I think this is what this is. Whereas the mineral P is very constant, is relatively more concentrated, and you need a much lower amount in kilograms per hectare. But the struvites, we still have a reasonably low amount also for some of these materials. But a factor that we can't go into in this short time period is, but the spread characteristics and handling characteristics of these materials are also important. So if we look at the P uptake from these larger set of materials in 2019, this here is essentially your reference set at 100%. This is where we use the mineral P fertilizer. And for these others to the right on the graph, we are substituting mineral fertilizer with P in cattle slurry, or from the struvite, or from the ash, or from the dairy sludges. And for struvite in particular, the news seems to be quite good, right? That seems to be at least as available, if not more available, than the mineral P fertilizer. And this is really important information to farmers, because some of the other options there weren't quite as available. And if we look at the end, how much did the soil test P change after the first year? You can see here what happens if you don't apply P, right? Your soil test P is going to be dragged down, and you can see here a situation where you have a crop growing without P and plus P. So P is really important for essentially food security at the end of the day. And the 2 struvites were boosting up the soil test P, at least to a similar extent to the mineral P fertilizer. So just to conclude, I think we can say that there is certainly a clear need to recover and reuse P from wastewater. Certainly there's a need for it at a plant production level within the EU. Keeping phosphorus in the loop really, if we think about our agricultural systems, our national systems, our global systems, and humanity in general, it's essential for long-term sustainability, and it lessens our reliance on mining up phosphorus out of the ground and all that's involved in that. That being said, that process is also necessary, at least currently. And Teagase, we are working on these plant availability and soil impacts of new recycled nutrient sources, and we're interested in such resources that might be coming from work that members of this organization are doing. A few other points to make, including things like the handling and spreading characteristics, the regulation of new products, quality assurance around those products, and cost structure are also key factors for farmers and need to be considered in trying to drive forward adoption of these practices. So with that, I'll conclude, and thank you for listening, and I'll stop sharing and hand you back to Ashay.
Thank you very much, Patrick. It's very nice and informative presentation, especially working with different bio-based fertilizer products to know what's the phosphorus availability and how it compares with the mineral phosphate fertilizer. So it's a nice presentation. Thanks a lot. And we'll catch the questions for your presentation later after all the presentations is finished. So please, all the audience, type your question in the Q&A feature so that we can follow up those later on. I move to our next speaker, Dr. Romain Lemaire from Veolia in France. So Dr. Romain obtained his PhD in 2007 at the Advanced Water Management Center of the University of Queensland in Australia on achieving high levels of biological nutrient removal from abattoir wastewaters using sequencing batch reactors. He's working at Veolia Water Research Center in Paris for 43 years as a research project manager on biological nutrient removal, and particularly on advanced nitrogen removal processes such as Agronomic, aerobic granular sludge, biofilm process, and also nitrous oxide greenhouse gas emission. He joined Veolia Technical and Business Support Department in 2011 as wastewater expert for the development and industrialization of new biological processes. He is in charge of process validation and support for business unit on design and build and operation wastewater projects. So please, Dr. Romain, take the floor for your presentation. And
thank you, Ashek.
Yeah, over to you.
Thank you. So I should be sharing my screen. So let me know if it's all fine with you.
Yeah.
Yep. Okay. Well, thanks for this nice introduction, Ashek. So I will be presenting. So my name is Romain Lemaire from Veolia HQ in Paris, and I will be presenting the overall approach of Veolia when it comes to peer recovery on the wastewater treatment plant sector. So we'll be focusing on that for the next 15 minutes. So the global approach we take at Veolia for peer recovery, it's based on obviously different unit. We are involved in wastewater treatment plant, but also in the final use of some of the product and even some of the agronomic value of the sludge. But looking at the first block, it's obviously the technology we can apply on plants. So BioP is key, as you all probably all aware, because the BioP can be then released in an aerobic digester and be recovered. So on development of new technology for BioP, I'm going to be talking about two topics just after. And regarding the P recovery, will be we have a Struvia process which can produce some mineral based on the phosphate, either struvite, but not only. Brushite is also possible, and based on what's the best for the plant, we can decide. And we have also developed the bioacidification process, which is targeting the P which is bound to metal and leaching this back so we can do P recovery even when bio-P is not employed in plants. And we have a first full-scale implementation in Germany undergoing at the moment. And active also on the recovery of P from sludge ash after incineration. The second block is obviously the operation of the plant, and bio-P being central, as we said, to P recovery, and it being a relatively complex process also to manage. We have developed a full digital advanced control system to optimize the bio-P at all time in the plant, part of the upgrade digital solution for Veolia. And we are also got expertise on plant-wide modeling, targeting again the P recovery, and it's a EU project we're working on, especially for the German sector, as they have a special legislation in place for P recovery with strong target. But we are about to do some full plant modeling and to do scenario, and I will detail that also in my talk. The other two blocks are obviously the product valuation of our end product in a wastewater treatment plant, typically sludge, but also all the mineral or the product we can recover. And we have a subsidiary called SED, which is taking care of that for Veolia. And we are collaborating with a lot of different fertilizer company to develop a specific fertilizer, P-based or not only, some organic also fertilizer. And we are working also with them for some technology for P recovery from sludge ash after incinerator. And the last bit being but not least, the agronomic research and development and valorization of those end products. And we've been involved since a really long time with a partnership with INRAE, which is the French National Institute for Agronomy. And we did some specific field tests, a bit like what Patrick was talking about, up with them for sustainable farming, those products. So you're active on all of that. I'm going to be focusing a bit on the first block, which is linked directly to the wastewater treatment plant. First is bio-P. So I'm not going to do a full 50 minutes on bio-P, but just one slide. So for all of you, understand the specificity for that. To do biological P removal, we need specific bacteria called PAO, and for them to develop in a plant, they need to have anaerobic condition, which is no oxygen, no nitrate, sometimes somewhere in the plant, quite often. And they need to cycle with aerobic condition, and they can use oxygen or nitrate to uptake the P. So they really speed, they do the opposite of what we want during anaerobic condition, but they store carbon in a later condition on the oxygen or nitrate. They uptake P more than they release, and the P is then removed from the water, stored in the cell, and we can get that P released during a digestion and do P recovery. But this is obviously what is key for bio-P in a wastewater treatment plant. Now, having that in mind, we all know bio-P classical configuration, which we call mainstream configuration, when we put an anaerobic tank upstream of all the biological tank in charge of the nitrogen and the BNR removal. And this is the traditional way to do bio-P, but it's sensitive to inlet flow variation. We change the retention time in that tank. It's sensitive to nitrate, which are recirculating into that zone, which is becoming not anaerobic anymore. And it's not really possible to retrofit a plant which doesn't have an anaerobic tank. It's difficult to put that upstream. We break the water line, and it's obviously a bit complicated and costly. What we've been working on for many years, especially with a colleague from Denmark, from Kruger, it's to apply this on the side stream. So we move the anaerobic tank from being the first inlet tank to a side stream tank, just on the recirculate stream from the clarifier, which is the sludge which is returned back to the main biological tank. And by putting the anaerobic tank at that place, we can have a more compact bio-P system so because the sludge is more concentrated. And with that, we are not impacted by the different variation of flow, and also we reduce the exposure to nitrate. So this has been very successful. It's quite popular nowadays, this side stream configuration of BioP. And we have been working on that for more than 10 years in Denmark. And it's something we more and more propose on project to do the BioP this way and not the old fashioned way. Another technology development we're working on is to move BioP into the compact biofilm technology. So you're probably familiar with the very compact plant we can have, like either the BAF or the MBBR when we have a footprint issue on the plant. It is compact, but there's always a but. It requires quite a bit of chemical usually, mostly coagulant for pee removal. It doesn't do BioP today. And also some methanol and polymer are sometimes required with this system. What we wanted to have is keep the capacity and trying to get BioP to have a full compact with no chemical process. And to do that, we've been working with the MBBR technology, but operated in a batch mode, so in an SBR mode. With that approach, all the biomass is on the media, and we can have an anaerobic feed and period at the start of the cycle, followed by cycling aeration and anoxic to do the most of the nitrogen removal, but also the P accumulation, because we have release P during the anaerobic period initially. And then we have just a draw of the effluent. The good thing about that is all the biomass is on the media, so we don't rely on any settling SVI of the sludge. We can draw most of the volume of the SBR at the end of the cycle. So obviously it's a very compact system. We're talking about 6 to 10 hours HRT of the system based on the concentration of the wastewater, which is quite short for this system. No risk of losing the biomass of the granule, a very high exchange volume ratio, as I told you, and no risk also to have nitrate leaking into the anaerobic period because we remove most of the water at the end of the cycle. As all the biomass is on the media, we do need a separation unit at the back end to remove the inlet particulate and also all the growth which is detaching from the media. And for that, we are using a special DAF which doesn't require any chemicals. And finally, we produce quite a bit of sludge. It's a very high rate system. So a lot of sludge, really good VSS, very good for biogas and getting energy back, and also very good for P recovery because we can get it back after the digester. And so we can bring BioP into the very compact biofilm system. So this is on the full scale demonstration today. We've done all the pilot testing and keep an eye on that because we hope to industrialize that process quite soon. Next part is about operation. So we do have within Veolia this digital approach to optimize your performance of the plant, different type of module or driver, energy production, weather forecast, and so on and so on. And there is part of that big upgrade suite. We have the biological capacity improvement. So it's we have a lot of experience with that, more than 25 years, especially coming from Denmark and Kruger colleagues who've been developing this digital approach on operation for many, many years. But if we look at what we have, especially for BioP, we have the smart BioP module. And what it does, it's to enhance BioP in existing volume and reduce your consumption of chemicals for P removal. What it means, even if you have a plant with no anaerobic zone, as I explained before, so no BioP happening, what this feature tries to do is to create a time for BioP bacteria to develop somewhere in your plant, somewhere in your volume. And how we do that is by real-time control of the aeration phases. We can create temporary anaerobic phases within your system during low load period and low flow period, as it always happens on the plant at nighttime or seasonal and so on and so on. So it's very adaptable to all type of activated sludge design, like a double ditch design as the historical Kruger design in the Nordic region, but also a single ditch like oxidation ditch system, when we will prolong the anoxic, the off time, to create anaerobic zone when load and flow allow for that. And also for your normal plug flow MLE recirculation type of plant, what this smart BioP will do is when load allow, we will reduce or stop, the nitrate recirculation to create a prolonged anoxic and anaerobic zone in this usually anoxic zone. So by doing all that, you can create BioP. You can have BioP in a non-BioP plant. So this feature rely on a lot of individual module, which has been developed for many, many years, and it all put everything together, looking at mixing, sludge edge control, the RAS control, as I told you, the nitrate recirculation, all those individual feature of upgrade are put together to address BioP in your system. An example to illustrate that, which might talk a bit more, is this is an upgrade smart BioP on a plant in Denmark, and you can see here we have the phosphate online, ammonia online in blue, and nitrate online in gray, and we can see the normal pattern intermittent aeration. And at midnight overnight, the load was low, and the smart BioP takes control and prolonge the anoxic time. And what happened is the P get released because we are starting to be deeply anaerobic, and ammonia is increasing because we are not aerating anymore. And when we have ranges, and when ammonia becomes a bit too high, then the normal cycle of aeration start again in this example, at 4 a.m. in the morning. But by doing that, for example, every night, what we can have is, so this is what happens. So the smart BioP is activated to 1 over that 4-hour period overnight, turn off, and you see the aeration pattern is stopped during that time. So we create anaerobic zone or time in existing volume when no BioP is happening usually, and we can get BioP happening. So saving on OPEX, so you use less chemical. If you dose chemical, you have less chemical. If you have tertiary P removal, that will be less as well, and you produce less chemical sludge as well. And on CapEx, you can have BioP without having to create a dedicated anaerobic tank on existing infrastructure. Final point for today will be this plant-wide modeling I was talking about, focusing on P recovery. So what we develop is a decision tool based on the Sumo platform. For those of you familiar with plant-wide simulation, you might know BioWin, West, which are alternatives, but Sumo allow you also to modify the code and code special process unit for P recovery. So we're using that to assess the fate of P within an existing activated sludge plant, model the plant, drive some upgrade scenario targeting P recovery, and look at what it gives. And that's really what we use that as a decision help maker for our client to make a decision which way to go with their plant. The way it works, we have a data for the modeling approach, data collection initially, like every modeling of a plant, you need to understand the problem, do the visit, use the site data, maybe do a bit more analyzing yourself to get the model going. Then we have the modeling and calibration of the model through the Sumo platform. Then we simulate some retrofit scenario while we're happy with the model of the plant to see what different scenario can do to this plant, either it's a pure BioP plant or a chemical plant or a hybrid plant. And finally, we have the report as a dashboard with some KPIs based on what is your main KPIs driver. Is it like in Germany, gram P, the target of 20 grams of phosphorus in kilogram of dry solid matter you produce of sludge, or the percentage of P recovered in your plant, and so on and so on. And based on those KPI, you can compare different scenarios. So it's an example of this tool. So you have your baseline scenario here, and you create different scenarios through the modeling, through Sumo. and you're gonna have your different KPIs. So the sludge looking at the TP in gram
Maybe
P per
one more
gram.
minute, Romain. Sorry, just
Yep.
maybe one more minute.
It's
Yeah,
my
please.
last slide. So and based on those KPI, you can see where you are and define what is your scenario, which is producing what you want. And for this plant in Germany, was ready to get below 20 gram P per kilo of dry matter, and one scenario could achieve that. So that's all for me. That was my last slide, Ashek. So if you want to learn more, you can you have few email contact here, and feel free to contact your people from Veolia in Ireland.
Thanks a lot, Romain.
So I give you back the.
Thank you very much. And it's a really lots about the process on new upgraded technologies coming up for phosphorus removal process. Especially the important aspect is biophosphorus removal recovery process. So yeah, as Roman said, if the participants have any specific questions later on, they can contact in the email address provided there. Okay, so yeah, please, audience, type your questions in the Q&A session. We are seeing some interesting questions. We'll approach those towards the last Q&A session. So before the last Q&A session, we have our last speaker, Mr. Matt Kuzma from Southern California. So Mr. Matt Kuzma has dedicated his career to focus on development, management, and commercialization of emerging technologies in water and wastewater segment, with a specific interest in recovery of resources such as nutrients, energy, and water. Matt brings 25 years of experience in the global water wastewater industry, primarily focused on advanced technologies such as membrane filtration and membrane bioreactors, nutrient recovery, anaerobic digestion, and advanced biological wastewater process. With a keen interest in travel as well as some time living abroad, Matt's working location include North America, Europe, South Asia, Southeast Asia, Australia, China, and the Middle East. In the past, he worked at US Filter, Veolia, Siemens Water Technologies, which is now Evocua, and Energia Organica Water, and recently rejoined Ostara as vice president to lead their efforts in implementation of nutrient recovery projects globally. Matt has a BSc in engineering from Miami University and currently resides in Southern California while working out of Ostara's Vancouver office. In addition to efforts at Ostara, Matt's ongoing work supports the Sustainable Phosphorus Alliance as a board delegate, and other forward-thinking organizations provides great opportunities to move the industry in a more sustainable direction. So saying that, Matt, please unmute your mic and take the floor for your presentation. Thanks.
Yeah, I think I'm unmuted here and shared my screen. So hopefully you can give me a thumbs up, Ashik. Good. Okay, lovely. Right. So truly the travel quarantine is over when you start allowing non-Europeans into your webinars even. So be nice if we could do these in person. But I'm going to talk today, as Dara mentioned earlier, about the project underway there in Dublin at Irish Water's Ringsend facility, where we're implementing the Ostara technologies. Just very briefly, a bit about Ostara and who we are, some context for the technologies that will be implemented there, and then of course how they integrate into the process configuration at Ringsend with all of the upgrades ongoing there. What we're expecting from a performance standpoint based upon the modeled feed criteria coming into our system. A bit about our fertilizer, and I'll talk about that in the next slide. But you know, Ostara is both a fertilizer company and a water treatment technology company. And then just lastly at the end, a bit about the schedule, because you know, quite often we get a lot of questions about where we are on the schedule for operation and implementation there at Ringsend. But as I mentioned, Ostara is a a water treatment technology, which is really the focus of this discussion, but we're also a fertilizer company in that the recovered fertilizer product that comes out of our technologies, we then take and commercialize as a mineral fertilizer in the market, and really view that as a win-win from the standpoint of improving water quality, but then also moving those nutrients that create eutrophication challenges and moving them into the supply chain on the fertilizer side. And really that becomes part of this, circular economy discussion and a circular economy movement. As was presented earlier, most of the fertilizer currently, or most of the phosphate currently used in the market is coming from phosphate rock. Certainly that's true in the mineral fertilizer market as opposed to the organic or I guess digestate and some of the other items that come out of biosolids and dairy operations, et cetera. But really what we're aiming to do is to increase the efficiency of the transfer through that supply chain. So if you look at traditional fertilizer mining, production, application, and then ultimately how it ends up on your plate, about 80% of that fertilizer is actually the P value is lost in that supply chain. So for every ton of fertilizer that is, or phosphate rock that is mined, only 20% of that actually ends up on your plate. And then of course, humans as a net balance, everything that we take in, we actually discharge once we've kind of hit full size growth. So ultimately, we're looking at nutrient discharges becoming an issue from a eutrophication standpoint. Greater urbanization and all of these things will certainly only accelerate that process. But Ostara, we're looking at intercepting those coming out of the wastewater treatment process, recovering it for sustainable agriculture. I'll talk a little bit about how the fertilizer behaves, and then at the back end, really bringing that sustainable agriculture into the food consumption chain, such that we can capture it again as it comes back in the wastewater process, all at the same time while reducing the issues related to eutrophication on the back end of the wastewater discharge. We currently have 22 systems globally. You'll see a heavy concentration in North America, some in Europe as well, one in the Middle East, in Tel Aviv, which is actually a relatively similar size facility to what we'll have at Rings End. But these have been, over the past, say, 10 years, growing, and actually the rate of increase is accelerating a little bit as we see broader acceptance and adoption of biological phosphorus processes, as was spoken about a moment ago, but then also a greater interest in anaerobic digestion for energy recovery, which is essentially an enhancement and or requirement for recovery processes such as ours to work. Just looking at the technology a little bit, I like to put this picture in relatively early. This is actually a picture of a Pearl 10K reactor in Edmonton, the same size system that will be utilized at Rings End. But if you look at the core technology, essentially it is an upflow fluidized bed reactor. So we will bring in this particular case, 2 feed streams into the bottom of the reactor. We'll add magnesium as the third leg of the struvite formula. So magnesium ammonium phosphate, lots of ammonia formed in the digester, phosphorus released under anaerobic conditions, and then we add the magnesium to remove the other 2 compounds. And in some cases, we of course have to increase pH a bit to form the crystallization reaction. But that is all done at the bottom of the reactor. And then essentially as it moves upward through the reactor, and the reactor gets wider at the top section becomes a clarifier and allows the struvite crystals to settle out at the bottom. The upflow velocities in here also wash out the organic solids that would be coming from, you know, dewatering centrates and so on. And ultimately those solids wash out of the treated effluent at the top. We do have a recycle line that takes essentially treated water at the top and reintroduces it at the bottom. And that provides us a couple of benefits in these scenarios. One is that we're not dependent upon the feed velocities or feed volumes to maintain our upflow velocity. We can do that, you know, through the recycle. And then the second part of it is that it provides dilution water that allows us to control the concentrations of the ingredients and therefore the rate of the reaction. And that becomes important as we look at supersaturation ratios and how to grow a large enough crystal that then settles out in the reactor itself. It's a bit oversimplified, but we do pull out of the reactor at the bottom. It's not shown on here, comes out of the reactor through a dewatering screen and a dryer, and then ultimately that dried product is put into the 1 ton super sacks. And I'll show a bit more about that in a moment. Now, across different applications, different size facilities, we do have a range of reactors, both in terms of configuration, size, and capacity. But for the purpose of this discussion today, I'm focused on the 10K reactor, which is the largest one we currently offer. And that will be going into the Rings End site. If you look at it, it's a relatively large, 16 meters tall, 7 meters across at the top. The application at Rings End will have a single Pearl 10K reactor. And then in the building, there's been an allowance for a second reactor if required in the future. As you know, given the discussion earlier about modeling, you know, we have found some inaccuracies and challenges in terms of modeling what kind of recovered content can be fed to our reactors. And so as we've discussed with Irish Water in this case and other clients, you know, we certainly recommend maybe considering space, but not overbuilding based upon model results, because it can vary quite a bit. But there is a space allowance so that if necessary, a second reactor can be added. And then also there's a fair bit of growth capacity available in the reactor itself for the upgrades ongoing at Rings End, both in terms of process and population equivalent treated there. Just looking at the building, you know, I do want to mention that for this project, it's actually being constructed and delivered by Murphy. So this image is courtesy of their design work. We're supplying the technology, but they're actually doing the on-site construction work. And if you look at the components that I mentioned previously, we have a magnesium system here on the far left. We'll be getting dry magnesium oxide powder that is then made down into a magnesium hydroxide slurry, is then fed into the bottom of the reactor. This is the single reactor. You can see a space just to the right for the second reactor if necessary, on the other side of the stair platform there. Once it comes out of that reactor, it'll get processed over at the dryer. It'll be dried to 99% plus dry content, so say 1% or less moisture. From there, it goes into a storage silo, and then from the silo into bags. And you can see the forklift there that will be then moving the bag product around. Star will be responsible for picking up that fertilizer product at site, and every time we pick up a truckload, we'll then be paying some revenue back for the value of that fertilizer product. Integration into the broader facility is of course important. So you know, if you look at the upgrades ongoing at Rings End currently, they are both expanding the facility as well as converting over to a Nareda process. Those Nareda processes historically have been very good at pea removal. So as the pea comes in on the far left, you'll see some primary sludge settled out, but then the Nareda process will essentially concentrate the phosphate into the biomass. that will get wasted out. Of course, in North America, we call it WAS, but in the UK and other parts, it can be referred to as SAS, secondary sludge. Will go into wash strip tank. That wash strip tank is essentially an anaerobic reactor that allows the phosphorus and magnesium to resolubilize. And as it's done, with the solids in the tank, then hits the pre-dewatering system where the solids are separated, we can bypass phosphate and magnesium around the THP and digestion process. And that becomes important to avoid struvite formation in the anaerobic digestion process. Magnesium is essentially the limiting ingredient. And as we release phosphate, we also release magnesium from the SAS. So bypassing that around means less struvite in your digester dewatering process and more struvite leaving in a bag as a revenue generator. So essentially, we can double the production of the fertilizer product in the pearl by stripping the P out upstream of the digester. So with that, then it'll go through the solids, the sludges will go through THP, digestion, dewatering. I'm not showing on here, but they'll actually be dried as well, the biosolids, before removed from site. But those two streams, the post-digestion dewatering liquor as well as the pre-dewatering liquor, will be the two feed streams coming into the bottom of the reactor. So a couple of objectives that Dara had mentioned, of course, one is avoiding the recycle loads that would come back from the untreated liquors. Will stabilize the biological, mainstream liquid treatment process, such that we can, help facilitate, meeting the effluent limits on the liquid discharge. We do also, by avoiding struvite formation and moving the phosphate away from the digester and ultimately the biosolids product, we can reduce the P content of the applied biosolids. And that becomes important. The phosphate content of municipal wastewater is out of balance in terms of nitrogen to phosphate ratios. So essentially, for most fields, when biosolids are applied, you are over applying phosphorus relative to the demand. So we've seen a lot of regulatory structures coming into place where that becomes a limitation, and then the cost of the biosolids management is increased as you need more and more land to dispose of the same amount of biosolids. So we do help reduce the phosphorus content of the biosolids as well. And then finally, if you don't do something proactively, quite often in any well-operated BioP plant employing anaerobic digestion, you'll run into significant issues with struvite, unintentional struvite formation. And the best analogy I give there is a kidney stone, where these same ingredients, quite often kidney stones can be either struvite or a calcium phosphate compound, depending on your diet, but nonetheless, that blockage in the system can be quite painful. Just looking at there's a couple of conditions essentially that were required in the tender process to treat. One was kind of an initial capacity, an initial condition, and then ultimately a future condition. And if you look at these two on the right, we essentially have an 11 ton per day production configuration with a single reactor, and then ultimately growing up to 14 tons a day, where a second reactor could be added. But looking at the kind of key highlights here, we're looking at phosphorus concentration in the say 300 to 400 range. From that, we can get a discharge requirement. We're required to be below 50 on the discharge from our reactor, which gives 85 to 88% removal. And then, as you'll see down there, we're expecting or hoping to make, say 4,000 to 5,000 tons per year of crystal green fertilizer in the process there. Just there with the crystal green, I wanted to talk a little bit about that product. It is a phosphate fertilizer, mineral fertilizer, greater than 99% purity. The crystallization reaction does do a very good job of avoiding other compounds. I'll talk a little bit about citrate solubility and root activation in terms of how it impacts some of the behavior characteristics. But it is, as a fertilizer, a very good product, the lowest salt index of phosphate sources out there, which actually helps from a crop standpoint, avoiding any burnout associated with salt application. Even though it is coming from a wastewater source, it's the lowest heavy metal content.
Matt, maybe just 1 more minute, please.
Yep, no problem. Lowest heavy metal content, even in comparison to mined phosphate rock products. So high purity, low heavy metals, and with ongoing issues related to cadmium, that will continue to be an area of focus. I've got 2 slides here that essentially show the same thing, which is that this one is leachate coming out of a fertilizer trial, and what you can see at the bottom is that crystal green application and control essentially ends up with the same result, as opposed to MAP, which is monoammonium phosphate application, where because of the high water solubility, you can end up with leaching of the nutrients that become a eutrophication challenge. And essentially, this is the same thing with a surface runoff trial that was done in the UK. At the bottom here, you can see crystal green and no fertilizer application, essentially ending up with the same result. And the function is that because the struvite is low water solubility, it only releases and becomes soluble and available to the plant as the plant demands the uptake, and it demands that uptake through the release of acids that then dissolve the struvite in the root structure. So it has to be applied into the root structure, but it does make it more efficient. And ultimately, because of that efficiency, you have to apply less phosphate to get the same crop results. So it's sustainable in terms of reducing demand and addressing non-point source runoff and leaching issues that can cause eutrophication. And then just finally, this is the schedule. Of course, we're in the design phase now and ordering equipment. Contracts were just signed a couple of months ago. We'll be delivering equipment over this fall and winter. Murphy will be finishing construction a bit over a year from now, and then we expect to be commissioning into the winter and maybe early spring of 23. So a bit less than 2 years from now, we expect to be up and fully operational. And with that, Ashik, I'm done. So I think I beat your timer by about 6 or 7 seconds.
Brilliant. Thanks a million, Matt Kuzuma. So brilliant presentation and lots of information and insight on the Wastewater phosphorus removal process and the product's performance. Really, really good. We already for original time, we have around 10 minutes. Maybe we can have few more minutes, but without further delay, we maybe approach our Q&A session, and we see there are some already questions posed. Please, the audience, if you have questions to the speakers, type in there and also type in who you're posing to. So I like to address question from the bottom, for example. So the first question is actually related to Matt Kuzuma and Dara White's work or presentation. So the question is, the audience is asking, previous plans to upgrade Ringsend wastewater treatment plant had an outfall pipe out to sea, while lower regulatory nutrient limits on discharge is applied. So the question is, with the upgrade process, would it discharge limits to surface waters in Dublin Bay without the need for this sea discharge pipe? So how this upgrade will improve that infrastructural system, which is currently taking all the discharge to the Dublin Bay? Would that have an impact there? Dara or Matt, you can address that question, please.
Yeah, I think Dara is better addressed that.
So I think I'm not quite clear in the question, but the EPA have designated the lower Liffey as a sensitive water, and that automatically brings under the Urban Wastewater Treatment Directive a TN and TP limit of 10 and 1 because it's well over 100,000 PE. So once the effluent is meeting that, and this was a kind of real point of attention in the environmental assessment impact report for the upgrade. Once a lot of modelling was done to look at the impact of the final effluent. So we are discharging just at the kind of sea end of Dublin Port. I'm not sure if that's addressing the question. I think it might.
I suppose with the upgradation process, of course, you are expecting to reduce your discharge phosphorus concentration. And if that is the case, would there be any further requirement to use those pipelines, which is currently discharging phosphorus to the seawater? Do you have any information on that?
Yeah, we're using the same outflow, and so and currently, we're discharging, I guess, about an average 3 to 4 milligrams per liter of phosphorus in the final effluent. So we're going down to less than 1, and our process proving has demonstrated that will be less than 1. And as it's a BIOP process, we have backup chemical dosing to manage the emission limit value to less than 1. So there'll be at least a 3 times reduction in the amount of phosphorus going into the river.
Thanks, Dara. So I suppose still the discharge would be there, but the concentration would be much lower. That's the main thing.
Yeah, the mass loading is much lower.
Yeah. And regards to Ostara phosphorus removal process, one of the audience wanted to ask if that process can also be used in pharma industry because they also have phosphorus residues in their wastewater stream. Matt, if you share any experience based on your technology using in different wastewater sectors, like.
Yeah, certainly it's applicable. Really, it can apply to any soluble phosphorus stream. So we have projects that are kind of ongoing between food and beverage processing discharges, corn ethanol, potentially in dairy, or other cattle and poultry applications where you're concentrating those wastes into maybe a merchant digester where you're covering biogas and then converting much of that into a soluble P content. But certainly on the industrial side, there are a number of streams that can be treated. We have to balance a little bit, both concentration has to be of a suitable concentration, meaning high enough, and then also, some of the P mass, but certainly it could very well apply in a pharmaceutical application.
Can you just a bit tell, like, what sort of concentration threshold you really require to install such a technology?
Well, a lot of it's driven by economics. So I wouldn't say there's an absolute, right? So the higher, the better. But, I would say once you get down below, say 40 or 50, it can be a bit challenging because your net benefit, just as a percentage, starts to decrease, and the cost of the chemical inputs relative to the amount removed will start to increase. We do have a project, for example, where the feed concentration is only 30 in a food processing application, potato waste. So there are some lower ones, but generally speaking, as opposed to a municipal wastewater stream where you may be 5, 6, 7 coming in, we're going to need to be a multiple of that concentration wise before the cost effectiveness kicks in.
Yeah, thanks, Matt. There is another question in regards to the techniques of Ostara or Estrubia. So the question is, did you see any improvement in the waterability of digested sludge when you use Ostara or Estrubia process implemented?
Yeah, so two answers to that. So one of the things that we find is without Wastrip, so just with the Pearl reactor treating the post-digestion stream, we saw about a 10% reduction in dry solids leaving the plant, and that was primarily through the offset of chemical sludge generation. With Wastrip implementation, we've seen a further improvement in that, and more so, well, one in terms of reduction of dry solids mass, meaning struvite formation in the digester, but also you help manage the mono to divalent cation ratios in the dewatering stream once you start bypassing many of those compounds around the digester with Wastrip. And we've seen about a 1 to 2% cake solids improvement with Wastrip, but it's really been driven by Wastrip implementation in terms of cake solids as opposed to Pearl on the post dewatering stream.
Thanks, Matt. So of course, this phosphorus removal process is very important, as we are also doing work bit on different bio-based fertilizers. One of the very common questions we are asked by the users, the farmers, like how available are these products available in the market? So we can see that the ring stint upgradation happening in Ireland, and that particular treatment plant can take care of 40% of wastewater in Ireland. My question is, how much of struvite product you expect to produce per day or weekly basis, and would that be available in the market to be used by the farmers, and when it would be then?
Well, we'll be operational just shy of 2 years from now. Based upon the feed conditions that have been given to us by Irish Water, we're expecting to make somewhere around, say 4,000 tons a year and that product is 12.7% P as P, not P2O5. It'd be 28% as P2O5. And yeah, we're very much incentivized to, we're responsible for all the cost and logistics of that fertilizer product. So, once it leaves the Rings End treatment plant site, any movement that we have out of Ireland or anywhere else just costs us money. So, we will very much be focused on using as much of that product as we can locally. And, that kind of fertilizer market development work is underway. We've already been doing crop trials in anticipation of this throughout Ireland for the past couple of years, working on developing that market. So yes, it will. Now, it will not likely be available as a consumer product. It'll generally go into the wholesale market, which is then used more for the large scale buyers, as opposed to being in your garden store down the street, where you as a with a backyard farm plot can access it.
Brilliant. Thanks. We are really looking forward to that as well. So hopefully that would add to the reducing chemical fertilizer phosphorus use in practice. So
it's very much part of our story, Ashik. We want to produce it and use it all locally.
Yeah. And it's of course, it's a very common question coming from the audience, like when we spread sludge or even digested sludge without any other processing, it causes runoff losses of phosphorus. So, and yeah, from the work, we can see that causes surface water pollution, even the river water pollution, eutrophication. So the question is, what do you think the regulations is coming up to strictly regulate using processed waste rather than the sludge or even the digested sludge going to the agricultural land? Do you think in the long term would that be a viable still, or it would be completely a change of the story? It's an open question. Even I think, like from agronomic point of view, Patrick may share some experience.
Yeah.
Hi, Patrick, you are muted. Could you please, yeah.
Yes, actually, I'm not sure I totally follow the question. Maybe you could just repeat the key
Yeah,
part.
I mean, the audience, some of the audience is asking, by applying sludge, is it still harmful in consideration that there will be likely phosphorus losses and that will deteriorate water quality?
Yeah, well, I suppose, at least from an on-farm point of view and its use, so in Ireland, farmers are limited in terms of the amount of phosphorus that they can use. So they have a phosphorus limit. So Matt referred to situations where phosphorus levels in soil perhaps were becoming elevated due to farmers using sludge products on a nitrogen basis, maybe to meet their nitrogen requirements. There's, I suppose, different settings, particularly where they have intensive animals and grains are coming in. This has happened. So I might be aware of the Delmarva Peninsula, for example, where they have a lot of chickens, and they were, basically the cost of sending that manure and its phosphorus out of the region is quite high. And so phosphorus was building up on soils because farmers were applying that chicken manure to meet the nitrogen requirements of the crop. So I suppose that comes to the ratio, and these technologies seem to be able to influence the ratio of nitrogen to phosphorus. I suppose back to Ireland, as I mentioned, farmers, the amount of phosphorus they can bring in is limited. So there is a strong incentive to use that appropriately. Also, the cost of the mineral fertilizer, as I showed in my presentation, is it's multiple times higher than that of the other nutrients. But I suppose there is a challenge with things like slurry, for instance. If a farmer's got to transport it over a distance, there's, I suppose, a bit of a challenge there. In terms of bringing in bio-based materials, the work that we're doing, looking at how available it is to the plant, that would be information that could go into the formation of a nutrient management plan to allow it to be used at an appropriate rate, which would limit its, I suppose, the potential for it to be lost to water. And I suppose one other thing to think about, of putting phosphorus onto agronomic landscape. I mean, I showed a picture where phosphorus was limiting for a cereal crop in that case. But if phosphorus is holding back the plant's ability to grow, it's affecting its ability to take up nitrogen, for instance, and therefore you have nitrogen available to be lost. And of course, the EPA do keep track of the areas of the country where nitrates in water are an issue, or phosphate in water is an issue. So I suppose it's putting the right product in the right place, the right time at the right rate, and fitting these waste streams into that is important, and also that regulatory framework about possible contaminants and quality assurance. I suppose not something that we're doing directly, but I suppose attention to that area is also important. So,
yeah, thanks, Patrick.
Few thoughts.
Yeah, thanks a lot. Regards to wastewater treatment process, of course, it's very common to use those chemicals, alum or iron-based chemicals to capture phosphorus, which ultimately ended up in the sludge. And we see a lot of sludge or biosolids used in agricultural sector, and which actually limit phosphorus availability. There is research evidence showing that. So in terms of then biological phosphorus removal process, so Romain, if you can tell us a bit, what is the upgradation stage happening? Is that already implemented in the commercial wastewater treatment plants, specifically biological phosphorus removal process, or is that still in the development phase?
I'm losing the sound. It's been very bad for the last 10 minutes for me. So I'm on and off. Can you hear me, or I can hear you very patchy? So it's a bit, okay. So let's try to, can you just quickly repeat, Ashek, because I've been on and off quite a bit.
So the question is, in terms of biological phosphorus removal process, what is the stage of the development? Is it already implemented in the commercial wastewater treatment plants, in the commercial companies, or is it still in the research and development phase?
So for the BioP in biofilm system, or in MBBR, getting BioP into a MBBR, this is not implemented yet. It's been fully validated on the R&D and prototype at pilot scale internally at Veolia, and we're looking at a full scale or prototype demo currently for that with a partner, Agronomic, as you probably know them on BioP. Regarding site bio, can you still hear me or? Hello? No, we can hear.
It's breaking up. Oh, yeah.
Yeah, that's
you can hear.
Pretty bad. Yeah, you can hear. Okay. So BioP MBBR not implemented yet, but we have done all the pilot testing and we're looking at the first prototype.
Thank you very much. So it's already, we are a bit over 7 minutes now. So I suppose it is a very interesting presentation from all the speakers. And I really like to thank you again, Dara, Patrick, Romain, and Matt Kuzma, for your interesting presentation, and also to the Siam Republic of Ireland branch for organizing this event. And of course, as I mentioned earlier, this webinar has been recorded and will be only made available on Siam website, depending on the author's permission to do so, and if there are no issues for copyright presentation. So thank you very much, all the attendees for attending this phosphorus removal and recovery webinar today, and also for your support of Siam and Siam Republic of Ireland branch. We hope you found the presentation very informative and will join us again. For details about future Siam events, please go to the Siam events page. The links are provided in the chat feature. So I'd like to thank you again, everyone, and saying that also taking goodbye for today. Thanks a million.
Thank you.
Thank you very much. Stay safe. Bye now.
Thank you.
Thank you for all your talks.
Bye-bye.
Take care.
Bye-bye. Keep safe and well.
Indeed.
So thanks a lot, Barbara.
That's no problem. Sorry about the connection problems, obviously, in the beginning. But if you let me know whether everyone's happy to be the recording to go up on the website, then I can let Jane know. But it's very interesting work.
It is indeed, yeah.
I went to a webinar, not a webinar, a talk about phosphates, and they were saying that, was it 75% of the phosphate rock comes from Morocco?
Yeah, exactly. So I think main in terms of the phosphate rock or mining is one of the big source in Morocco, and then China and some parts in America. And literally, I suppose in Europe there is very little phosphorus mine rock. So here is over 90% is imported. So there's the challenge for future.
And I think also the artificially produced phosphate again has problems with with the impact it has environmentally on ecosystems as well, doesn't it?
Yeah, it's a bit of paradox. Like it's a limited resource, and then we are seeing a lot of loss in the surface water in the river, and causing water quality damage as well, especially eutrophication, algae growth, and deteriorating the water quality. Because ultimately, if the river water is getting deteriorated with the eutrophication, that is again expensive to treat that for our drinking water supply. So it's a bit of, and then again, destroying the quality of fish life or aquatic life, because when those algae and the vegetation dies, that takes up a lot of oxygen, and it reduces the oxygen level in the water. So yeah, it's a paradox. We have a limited resource and we have a waste there again with the same thing.
But the circular economy is good. Reusing the waste.
Yeah.
And
effectively
preserving the finite materials that we need.
Yeah, yeah. It's a very important issue now, actually.
Yeah. Anyway, it's nice to see you, and keep safe and well.
Thank you very much,
Thanks again.
Barbara. See you later. Yeah.
Take care now. Bye.
Take care. Bye now.